Hello, everyone. I'm sure you're doing awesome. So, in our last session, we took LLM as a stateless function, and what it was doing is predicting the next token based on the input context. That is on a very high level. We understood the internal architectures as well, like the basics of the tokenizations, the basics of the embedding, and the attention mechanism. So, if I have to just write them, so this was our primary focus in our session one. Okay, so in our session one, and not only session one, the subsequent videos that we had, which were kind of an extension to the session one only, like the application that we have built and the Olama, which we have used for to replace the OpenAI calls with our locally hosted models. So now in the session 2, our shift will be little bit shifting, and our shift will be towards the probabilistic nature of the LLM. So if I have to say in a very crisp words, what we are going to do is we are going to learn how to program this probabilistic machine, like the which is the LLM, right? Like we understood that we are putting some function, putting some input to the function, and we are getting some output. So how to program this probabilistic machine using English language? Okay, using English language, or like you can even prompt into the other language. I'm not going into that, like these days LLM support different languages, like you can even try to ask whatever your mother tongue is to respond in that mother tongue. It will keep on responding to that. So if I go by foundation, we will come what a GIGO is. So f- by foundation there is a function, and whatever the input that we are giving, that input will be passing into our LLM, and then we were getting a certain output in terms of token, and then the token would be converted to a string as per our requirement. So this leads us to a very simple principle that is called GIGO. GIGO is nothing but garbage in, garbage out, and GIGO is the iron law of AI engineering. So why I say iron law? So it simply tells that I'm not going to fail you. I'm not going to fail you, but if you feed garbage to me, like the data or the prompts that if you are giving, if that is not up to the mark, garbage to me, I'm going to put garbage out. So this is a simple funda of the LLM and the prompt engineering that we have in terms of the foundational truth, that the input tokens are the only state the model has access to. So there is no hidden database, no persistent memory, and no external knowledge beyond what you are providing in your exact request, right? So it is not that some sort of a API is doing some sort of a magic behind the scene. Rather, the truth is very simple. Unlike any traditional software, like where the bugs are deterministic, the input always produces that bug. LLMs are probabilistic. Okay. So with the LLM, like unlike in the traditional software, what happens is like whenever we are giving any sort of a any sort of a bug, suppose we get from our QA team, so we know that if we perform this step 1, step 2, step 3, we are going to get this. But LLM, being a completely non-deterministic or a probabilistic, it might happen that when you are feeding the same input, you are getting different output with same input. The model might hallucinate at multiple steps. So there are many reasons to that. For example, the first and foremost thing is like the probability distribution that we have. It like towards the to larger context size or the chat window. So the more you start like a single chat, the more you make it larger, you might see that the hallucination or the flattening of the responses gradually become worse and worse. And this is what we call the great hallucinations of the AI model. So these days the models are becoming definitely better and better, and how they are making it better, that also we will discuss. But the idea is simple. Like the moment the probabilistic, the PD which I wrote here, it is a probabilistic distribution. The more your context window or the more abstract thing you keep on feeding of different fields, your AI would start hallucinate on that. So let's take an example of the banking application chatbot. In that chatbot, suppose you are directly making a LLM call. You are not having any kind of refinement layer. So when you are making that LLM call, that means like probably to the OpenAI or in the Gemini, anywhere you are probably making that call directly with this input. So what is happening if we see internally from the LLM perspective? So this could mean multiple things, right? So first of all, it could mean that there is a pending deposit not reflecting in the balance. There can be like somebody already done the wire transfer completed, but wire transfer completed but not showing up. And it can be even a simple UI bug. Like the user just have to refresh the page. They are not refreshing. That is why it is not coming. The it could be some kind of a data pipeline issue, like the data pipeline is not publishing the latest transactions. So it can be variety of things, right? So but what it might do is, like, if you give this sort of a vague instructions or prompt, it would just give you a simple answer that deposit takes 3 to 5 business days. Okay, it doesn't even know whether you have waited for the 3 to 5 business days or not. But it might answer you that deposit takes 3 to 5 business days, and also there can be something like check with bank. This sort of very vague replies you can get, and this was one of the problem, like when all the big e-commerce, the fintech organization, they started to roll out their AI chatbot when the AI wave came in, but it was so much buggy simply because of this sort of things were not taken care, like the input that were given, they were not sanitized properly. So in this case, what happens is there is a very great traditional flow that we take. So that is being known as something called classification layer. So classification is only one of the way that we are going to see, but I will just tell you gradually what this classification layer would do. So suppose you have this user input to be transferred into LLM, but before that, if you could actually um, have another layer where you are classifying what exactly this problem or this user issue might be, that would save a lot of hallucination probability. So instead of this single prompt request, we are going to add this classification layer. And if you see over here in the step 1, what we are doing, we are going to classify the user intent, and that comes as a pre-processing. So we, like, this is just a comment. What we generally do is we use a smaller or a faster model, or even some sort of a decision branch within the application only, or any kind of rule engine to make a classification segregation. So classify this banking query into one of the below categories. So it is a deposit issue, or a withdrawal issue, or a balance display, transaction history, or others. And then what would be your output format? Your output format will be in a single word, the category name. And once you have built that, then our step 2 will come. In our step 2, we are going to mark this category specific context injections. So if we see this, what this guy would do is, this guy is going to take the category as the input now. So this was our step one. In our step one, we have make the classification and got the category, and this category is being fed into here now. And after this category is being fed, we are going to create a context map. Like if it is a deposit issue, if it is a balance display, what would be the actual prompt? So we have a lot of prompt like this, and using those prompt, we are going to create our system prompt that like you are a banking support specialist, this is your category, this is the relevant context, whatever the context map that you are getting, checking the pending request or deposit, this typically clears in 1 2 business days, and what exactly is the user input, and then you provide the specific and actionable solution. So now if you just see the full pipeline over here, you are giving a user input of money not showing, and the category at first we are getting, the category we are feeding into this from here to here, and using all this contextual prompt that we are building, that prompt is getting fed into the LLM call. So just take a pause and understand, previously we were just taking the input and we were making this LLM call, and now what we are doing is, now we are segregating the categories, and then further we are sending it for the LLM calls. So the funda behind that is very simple. Um, the the classification that we are doing. So whenever something is classified, classification reduces the entropy. So entropy, again, like it might look like a jargon, but entropy on a very high level, what it does is it tells you that there will be lesser uncertainty. So entropy is defined by the disorder or the uncertainty, and whenever classification is used, classification always reduces the entropy in terms of the AI engineering. So whenever you see much randomness around you, this is one of the theory that we need to put into practical in our AI engineering, that whenever we see a randomness or the disorders, we have to make sure that our classification is being done properly. So why this works, if I have to narrow it down, it is narrowing down that 5 plus possibility into one concrete one, and the context injection that we did here, this is the context map, and from that context map whatever the category we got, using those context injection based on the classification is one of the great technique that where the disorder or the entropy can be reduced. And also it is a two-stage design. So the moment you are using a two-stage design, why it is very much preferred is, instead of one expensive model, what we generally do is one cheap model for our classification we do. Okay, and the system prompt we built and then moved on to a like a further expensive model. So this is what exactly we do, we break it into a two-stage design, and this makes complete sense because it it reduces the cost. Earlier the amount of token that would be generated with a very abstract uh, request that you get would be way more, because token, as we discussed in our previous videos, that token is the currency of the AI engineering system. So as a developer or as an architect of AI systems, we always have to keep in mind that how can we reduce the tokens. Okay, and here the extra classification call, although it might take a little latency, but it improves the accuracy and it reduces the hallucination rate also. Okay, so these are the basic advantages that we have. The classification call will be probably some extra dollar we have to spend per request and a little extra latency, but it will definitely going to improve our accuracy, and this is measured by eval. So eval is something that we are going to cover in our later videos. So but just to give you some basic idea, eval is nothing but like it's a human evolution, because evaluation, because you like always capturing the semantic correctness through the automated matrices are very difficult for the LLM system. So just to make sure that the information that is being given are factually correct or relevant to the user intent, or free from any kind of hallucination, and also relevant to the domain. Like, then there are so many things comes together, and everything in the AI engineering workflow, we generally have a human centric approach to uh, judge whether the accuracy and the factual correctness have really improved or not. So in production system, like suppose any medical scan analysis or insurance claim processing, suppose you are doing a AI engineering pipeline. Okay, so human eval is a gold standard that you must do. You cannot say that okay, I am firing everyone because like this particular bot and this particular system of flow I have developed, but who is going to market that this is the gold standard that you have developed? It is this, it is being done through the human eval. Okay, so I hope by this time you are quite clear about why we were calling it as a garbage in, garbage out, and how using classification, that is definitely one of the technique, we can reduce the hallucination. So let's take this scenario, which is actually one of the very popular discussion in any kind of podcast you see, or any kind of the recent interviews where you might go as a AI engineer. So you are the architect for a national bank's customer support chatbot. The system receives around like 100,000 queries per day, and the current architecture sends the raw input to the GPT-4. So it is the same thing that we saw here over here, that it is receiving so many calls and all the stuff it is directly sending into the GPT-4. So 30% of the responses are generic and unhelpful. Like, this is being done by the human eval that we just talked about, that the responses that are being generated, this is kind of uh, not helping the customers by any means. And 15% responses are hallucinated. I just made up these numbers. And the average cost per query is quite high, like 0.05 per query. So even if like we have a very considerable amount of queries, um, with this 100,000 is nothing in terms of when a global bank is rolling out something, like in a country like even India or United States, anywhere. So it is becoming 1.8 million. That is the kind of cost, but it is not attributing anything to the business because the responses are not helpful. So the challenge is, leadership tells you that, look man, you guys are a LLM team, but you will be fired unless you reduce this cost, because whatever the money or the whatever budgeting we have, you have actually surpassed it to a large extent. And my question to you, or my challenge to you would be that, from GIGO perspective, why this current architecture is failing. If you could explain that, take a pause and just do some kind of a remind what you have learned so far. Maybe it will give you the idea of why it is failing. Then we will come to the discussion how we could make it a robust and a cost efficient system. So I hope you gave some thought. Now coming back to this, why this from the GIGO perspective it is failing. The first thing is that there are so many typos, slangs. um there can be even incomplete sentences, or the irrelevant sentences might go to the expensive model that we have hosted. And also there is no context augmentation. We are not really creating any kind of a system prompt there, right? So no context augmentation is being happening against it, where we will feed some of the basic banking policies. And there is no output validation. For example, anybody could come and start chatting about his own life problems into this banking application, because we are not doing any kind of output validation as well. So the input validation, typo, slangs, this thing will be coming under the input validation. The context augmentation and output validation also we are not doing. And alongside that, another main problem is, like all queries are of same weight we are considering. So Suppose somebody has lost money in some kind of a banking fraud. Their um, their request has to go through the highest priority through the banking system LLM, right? So we are not having any sort of a rule engine to divide them into weight. Like if it is a fraud related query, then just keep it at the top. So how would you make changes into the current architecture? Let's see. So this is the architecture in place, and let's talk about it. So what happens is, like now in our revised architecture that we are going to build to solve the problem given by the business, that you need to change this XYZ things, right? So this is what we are going to do. And the first and foremost thing, like whenever the user query comes, so we are going to have a tier 0 into that. So you see, into the tier 0 we are going to have a FAQ match sort of a thing. So we just going to see that whether that query which is sent is coming into any kind of FAQ category or not. After that, whether it is a account specific query. So if it is an account specific query, then we need to have the database, right? So in case like user is inquiring about their balance, so definitely from that database we need to go and fetch it. And if it is further more complex, then we are going to go to the tier 1. So now here in the basic classification, if you see in the tier 1 that we had, okay, so the through the FAQ match and through this database, in both of the cases we are already done with the basic sanitization, okay. And once we determine that okay, no, it doesn't come under the FAQ or the account specific things, then we put it as a complex one. So now complex one go to the tier 1, and here the real classification happens. So they then, if you remember the way we wrote, right, like we asked this guy to classify, so we are going to put the classifier intent over there, and then we are going to retrieve the context. So when we say retrieve the context, is basically setting the context that we did from the context map. So after, at this level, you see how strong our query is. All the basic things are being taken care by FAQ and the user data, and over here we have already classified our query, and then it goes into a context retrieval or RAG. So what RAG does is, RAG again another layer of retrieval augmentation generation that we will come into our later videos. In RAG we are going to get all our relevant context, and from the tier 1 we are going to inject the complete context now. So not only the prompt context that we have built, now whatever the context we got from the RAG, okay, there might be a vector database behind the scene. So just understand that this context is maybe another kind of a DB, which we call it as a vector DB. So it can be any kind of things like the recent Pinecone or Microsoft Phi, those sort of things can be there. Now this guy is going to inject the category and the uh, retrieve context into the actual prompt construction. So here the actual system prompt construction will happen with the classified data, with the RAG data, and with the system flow instructions. And at this level it would go to the GPT-4 or Anthropic, whatever the LLM that you have decided, and then it will get the raw output. And there can be some sort of a fallback mechanism in place, like in case I didn't get the response, probably we will do the uh, we might need to have a fallback, and then we are going to retry with the error feedback. And this error feedback we are and our validation layer can be multiple. So if the error feedback, like even after multiple retries it is not giving us anything, so then we are going to convert it into like we are going to connect it to a specialist call by converting into a separate call or a chat socket towards the support associates. So here you see this whole thing that we have designed, that there is a retry, there is a retry with the error, there is a fallback, everything that we are getting. So you could see that how robust this architecture is. Like It is although like you take a pause and take a screenshot, and you maybe you can zoom it out. So this is the actual real world chatbot, how they work. So if you are getting into this sort of a questions or this sort of a problem statement in your organization, how you are going to implement a certain AI chatbot with your domain. So this is the exact architecture generally we do. We go to database, we go to our vector databases for RAG, and then we build the context, and using that we are going to generate the final prompt, which we are going to feed to our LLM, and from the LLM we are get the output validation. So I hope that this part is quite clear to you now, that what it would do. Now let's come into hypothetical numbers that we might be thinking that what would be our expected outcome in terms of the cost. So this is, guys, again kind of a made up number, but the cost per query, if you see over here, have really reduced because you are right now resolving many things from the FAQ and the database. So it is almost reduced by more than 50%. The daily cost that we see, so based on this only, it started reducing, and 1.17 million is being saved uh, if I just compare it with the actual cost that we saw in earlier case. And for the generic responses, like probably generic responses will still be there, as I said, like through human eval we might find that there will be around maybe 5 to 8%. So that is again a great reduction. And hallucination will of course reduce because the classification and the other layers with the definitive outputs are being given. And right now the average latency will also decrease. So in this case the latency might increase for the one which are going to GPT-4, but the overall system average latency, if I see based on the one that are being hit into the database or the one that are being hitting the FAQ documents, it is going to be way faster. And our FAQ hit rate is 30%, so it is going to give like a instant answers. So here you might be having kind of a fail-safe design, but there are a lot of things when you are going into production will come into play as well, like monitoring is something that we really need to take care. For example, when we need to see that which tier handles, how each tier is handling the query, and which tier is taking the highest amount of time. Based on that we have to scale. So this is all, as a AI engineer or the backend engineer, you have to do in this system. Your scientist, the ML researchers, they are not going to do anything like that. And we are also generally this sort of systems goes through some kind of a A/B testing as well. We compare the response quality across the tiers, and not only the tiers. For example, if you want to call the Anthropic against GPT, against Gemini, how exactly how good they are faring for your domain. So like for example, simple image analysis, I have seen GPT 5.2 has a tremendous feedback, which even Gemini doesn't stand much chances. But Gemini shines in many other cases. Also, there are things like caching. So we have to cache the LLM response. Suppose the similar sort of things are coming. So those caching sort of things we could further improve the application performance. And the rate limiting, like suppose we see that from a certain user a human handoff is happening which might have some malicious intent, we can stop it then and there. So in session one of the way we explored LLM is it's a completely black box, right? So there is a API that request that we were just sending it over the top directly to the LLMs, and those LLM then would give you some sort of a response back, and that will gradually flow to your application. So through your API, you are calling LLM, right? And how we did it, like we just plain simple string we passed, but that is not exactly true for the production APIs. In production APIs, how we are going to engineer our prompt, that has a separate structures, and that we have to comply with to get the best performance out of it. So similar to the other markup languages like YAML or XML, LLM also has a very specific markup language requirement, which is being known as ChatML. And any modern LLM API, so any modern LLM if you are talking about, it expects the input in this ChatML format. Okay, so like how you are going to send the data, there is a particular format it gives you, that there will be a role of system. We will go very detailed into this, how this system, user, all this role can be used, or assistant. So assistant is basically the response that we get. Okay, and then the content which would come as a actual text. It can be like JSON or a simple text file. So this is this is the message object that the LLM APIs expect. Okay, so when you call a OpenAI, like models like GPT-4 or GPT-5.2, you must format the input as the list of messages in this chat ML style. So again, just to emphasize, like this is being called chat ML, like chat markup language, and you don't send a raw string the way we have been doing it in the other place. So there also we were in some way setting up the message object, but I was not putting it very explicitly to you because I didn't want to overwhelm you at that point of time. So we don't send a raw string in a single prompt. Rather, we send the complete conversational context. So how this messages array is being passed, let's take an example implementation. Okay, so you see this chatml format for this one. What we are doing is, like when we are calling OpenAI APIs, we are going to say that you use this model and then forming this message object. This is the most important part, guys. Okay, so we are forming this message object, and here we are having role, and then the content that we are sending as a system, what is a system prompt, and as a user, what exactly is the question that you want. So what you cannot do is, that is also we must understand, like you cannot do something like this. In Python, you just send like a response where you are in the prompt you are passing 2.2. It's a completely invalid parameter. Rather, you have to send it like this with proper role, and with proper chatml format. So here, like if you do something like this, like the people who have been developing it for some time, they will know that this is the most common error that they get, like whenever working with the chat, the OpenAI APIs, that this particular model doesn't support this sort of request, because chat models are not the completion models. Okay, so now how would you create a very simple weather bot which takes a single instruction, that how is the weather in London? Suppose you are a sarcastic weather bot. Okay, so you want to set some tone that you are a sarcastic weather bot who somehow gives the accurate information. Okay, so this comes under your main system prompt. Okay, and user, so this is your system prompt, and then there comes the user prompt. Okay, so what users will do, like user will give you this one, right? So the user prompt will be something like this, that what is the weather in Hyderabad, suppose. Okay, and then there will be like a assistant or a definitive reply that we are going to get. The reply we will get in terms of a content, like so suppose the reply we get, uh, it is just usual drizzle. Okay, and over here the important thing is the reply. How we get under the assistant. Okay, so suppose this is the turn one. Okay, where you are setting the setting that what kind of bot it is. This is the first thing at the system level you are setting, and then this is the user, and this is the assistant or the reply that you are getting. Now in the turn 2, the very interesting thing is that you have to include all of them, like this and this three you have to include, and then you have to append the message, like the messages that will have, you are going to append all of them all of them together, and on top of it there will be another user message. So this is the done, right? So there will be another user message. So this user message will be uh, like again, role will be user, and the content will be, suppose you want to ask that should I bring an umbrella, for walking, something like that. Suppose you want to ask that if it is raining in Hyderabad, should you really bring an umbrella, or it is just a small drizzle which you can get away without it. So now when you are sending this to your chat completion models, like when you are sending this to your client dot chat dot completions, so here you have to create the model. You have to mention the model, like if it is, for example, in our case, suppose it is GPT 4.5, and then in the messages, all the messages that you have been sending so far. Okay, so this all things will come together in the messages. So in the messages, again, what are the things that will be there? So this guy will be there, this user will be there, this reply will be there, which will be put as a role of assistant and a content, and then again a role user will be there. So in the turn 2 also, so this turn 2 also, whatever we are sending, it will be summation of turn 1 plus turn 2. Okay, so in these messages, whatever the things that we will be building, it will be turn 1 plus turn 2. So let's see it in like a simple example, how the code would look like. So code would look like something like this, that you will be sending all the messages, and the response that you will be getting, you will be putting it into the assistant. And so here it is the same thing that we were doing, guys. Like the first role is the system, it is setting up the system, then what the query that the user sent, then what is the response came into the assistant, then in the same messages object we will keep on appending this whole thing. Okay, so the response that you see, the chat completion, create, everything we are getting, and in the response uh, in the response, again, as a assistant role, you are going to get the whole data. So let's see the full picture now that we got how a basic multi-turn conversation would work. Okay, now this is a super simple implementation of Amazon's customer support bot. So what would happen over there is, you have a client, you have set up a client system prompt, and using that system prompt, you are going to make the call. But in this process, at first you are going to create the messages role as a system. Then suppose you have a complete history, right? Like in ChatGPT, you have a history on the other side, and your whenever you are pulling up a chat, you will see that there is a certain time it takes to bootstrap it. So generally what it does is, it gets the conversation history completely, and the message will get the conversation history, and it will be put like this over there, and then we are going to append it. We are going to append the message, the role is user, and the content will be the new user message that it will be passed. So whenever a new user messages will come, so here you see this new user message is being fed into here. Okay, and this is the conversation ID, that conversation ID will be pulled into. So all these messages are being built up, and so now the system we have, now the actual history we have, and the latest message we have, and then we get the response after calling like this, and in the response message content, you are going to get the assistant reply. Now, next time when you are going to make the call, what we do is just connect the dots now, guys, that under the role assistant, that I got an assistant reply, this part, you we are going to save our message, and then we are going to again get the message from there. So in that process, what would happen is, as a assistant message, it will automatically be saved in your conversation history, and your whole context will get built up. So this is, in a very nutshell, uh, any bot that you see, whatever the thing it is doing behind the scene in terms of the conversation history or anything, it is pulling the data from somewhere, and then it is sending it to the LLM, and all the classification and the other details that we talked here. Okay, this is kind of cherry on the top that we have to keep on building according to our requirements, so that the model doesn't hallucinates and the other thing doesn't happen. But this is how we are going to build our messages that we are going to send to our LLM API clients. And the simple, like, what we don't do, we need to understand that as well. So this sort of pattern is completely completely we shouldn't be doing. So if we just load the full history from the conversation ID, it will just keep on increasing. Okay, so here generally there is a particular pattern of summarization is being used. So whatever the, again, it comes under the classification. So if the message becomes a little bigger other than the system prompt, all the things that you are getting under the history, so this guy gets summarized. Okay, we will come into these things in a way more further granular manner, but I hope you got the idea that how Amazon customer support bot, or a simple like multi-turn weather bot, how you can save the data. You are going to save the data in any kind of persistent storage, and you are going to get the data for that particular conversation ID every single time, or in an incremental manner. So this is a very basic architecture that we were talking about. Like, user going to send a request to the app, and there will be a database or a Redis cache. You are going to get a truncated history. So this is a very important point, like not the complete history. Then your context will automatically overflowing. Then we have to build the message, and this particular thing, there is a technical term to it called bounded context that we just discussed. This thing is the bounded context that we have built up, and this bounded context will be sent to the LLM, and whatever the structure response we get, we are going to save the new turn. So here also we did saving the messages. So this is exactly on the coding level. This is how we are going to build it, and in our earlier example we talked more about in the architectural level. So now, this is the anti-pattern that we also talked about, like we never load full history like in a unbounded manner. So that will completely blow up our context and all the other controls that we might want. And one of the other part that we must understand in this process is the logical structure, like that we have, like the role plus content and whatnot. All these things are kind of universal across the model. Like when I say universal, that means if you are using OpenAI, if you are using Llama, or anything like Mistral, all kind of follow the similar thing, the Anthropic as well. But uh, how internally the tokenization happens, that is different for the different uh, mm, uh, the frontier models. So some model requires like special delimiter token, but all these things should be generally handled by the internally by the API endpoints only. So we just have to follow the documentation, regarding the role, system, content, whatever that is being given there, and it should work in that particular way. So as we gradually understand this prompts more, let's talk about the system, user, and assistant which we used earlier. So system, as you saw, like it is a system-wide thing. So what it does is it sets the behavior. The user, what it does is it takes the question to be passed on to the LLM, and the assistant, it holds the response. So although the response might come in different way, like it can be a response array, you have to take the 0th element of the array according to the documentation you need to follow for all the frontier models. But what it does is it holds the past response when you are sending it into your chat hierarchy, like from the turn 1 to turn 2 to turn 3. The assistant will keep on holding that what has gone for this particular uh, prompt response. Okay, so if I have to mark it in a tabular format, so system, do we need to include in the API call? Yes, every single time. The system has to be there. It sets the behavior rules. User, yes, for all the API calls, we have to include it because um, it is the most important thing. Like, what is the user message? So system, we are sending it only once, whereas user, in all the turns, we have to send the user message. So it shows what the user has said. And what about assistant? It shows only the past responses. So that means it like, other than the first one, like the system isn't there for the first one. If I have to simplify it more, it is something like this. The system that we see, okay, so the system is in only the first one, and the assistant will be in all other than the first, because whatever the response that we are getting, we are keep on feeding it to the assistant. So the example that we took earlier, if we see, we generally got the history of the whole message over there, and after getting the history, we extended that particular history into our messages list or messages array. So what has happened there is, the all the user and the assistant messages that were coming through, everything was included there, and it includes both user and the assistant messages in the history table. So it is our responsibility as a AI engineer and a developer that in our history we keep on storing the user and the assistant messages. So if your conversation is like this, that there is a user, there is an assistant, and then again you are this is the turn 2 what we are doing. Okay, so this part is the second turn, so this part is the first turn, and then this part is the turn 2. Okay, so turn 1, and this part is the turn 2. Now the interesting part is, when you are sending the message after turn 2, so when you are sending the actual turn 2, sending the turn 2 to API call, how it would look is, the like, all the messages that we are going to send, it will look something like this, that the roles that we will be sending, for the first one, the user content, where is my order, and then the assistant response, and then again the user. So ideally, like your history call or the get conversation history that we did earlier, right, this part, this is going to take care of the uh, this sh- this get history should take care of this part of the first two messages, and then further you have to populate the third one. So it is just like list append, whatever the list you have, you have to keep on appending your rest of the stuff. So if I have to give it a complete thing, so how it would look like is, it would be, when you are getting your get conversation history, you should get the past messages, and further the whole system of messages would look like this. The system prompt will be there, then the user assistant and the user. Okay, so now that we were talking about, like, conversation history a lot. So how generally this conversation history table looks like? So if I just do it in a very high level, so there will be a conversation ID. So for example, in your chat GPT, suppose you have all the past conversation, every conversation has a different conversation ID, and against that conversation ID, the complete user assistant, all the turns and everything will be saved in there. So you probably you can understand with this how easy it becomes, that suppose in a some sort of a NoSQL database, or even in a RDBMS, if you want, you can store all of your conversation turns, like the user assistant, the system roles, and everything there. And then gradually you can just pull in that conversation ID, you can order by the timestamp, or you can put everything ordered by the timestamp itself. So all the time this database should return the result which is completely sorted by time, and you are going to keep on getting the actual conversation history. And of course there are the like the compaction or the summarization, those things are there. So what happens in every LLM call, if I just have to do a small recap, that you send a messages, that list extending with the role user message, and LLM responds with the role assistant. So this is the key, guys. I hope it is clear to you what is the role user and what is the role assistant and what is the role of the system. And you must store the assistant response. So in this user assistant, all these things should be stored in that descending order of the time, and the stored turn becomes the part of the context for the future interaction. So this is again one of the very fundamental requirement of how our AI engineering bots generally work. So uh, gradually we are coming from the high level to further lower level, how this call happens and how we can further optimize it. So the new message in a conversation, how is it handled? If I have to take a full loop recap, so at first the new messages are being sent, like as you have said, as you have seen earlier, like suppose in our previous message we are asking that is it out for delivery. Then in a follow-up message we are asking that will it come before noon. So it is going to get again the history, and you can again compact it, maybe the history, the top four messages. Then you are going to build the message, and further we are going to send it to the OpenAI chat completion. And then once we get the response, what we do is we put it into suppose we get it into this choices zero message, and there are a lot of other things will be there, like the probability, the confidence, everything you will get there. And then in the database you are going to save it as an assistant message. Why as an assistant message? Because the moment you are saving it like this, when we are getting the the past responses, it will be very easy that we get and append as it is. We do not have to do any further processing on this. So the assistant messages, we will just get it and we will keep on appending it into our message history. So if I have to oversimplify it for anyone, the idea is always we have to keep on optimizing the state management. So behind the scene, it is nothing but a state management. If I take this again practical example, why I'm taking further more and more example, because this has to completely solidify it in the mind, so that any system that we develop, this is the basic principle we always follow. So in this practical example, suppose again a multi-turn conversation is going on. So initially you have sent all the details, like this is the system, this is the user, and this is the content, like how do I read a CSV file in Python. Okay, so you are chatting with someone as a Python expert, some chatbot, and you are asking that how do I read the CSV file. So the response would be like the model will be the GPT-4 here, and you are sending the messages, and then you are going to store the assistant message, and in the turn 2 you are going to append this particular message there. So what happens is, whatever the assistant message you got there, look, in the messages you are going to append it, and then whatever the next user role that is coming in, that we are going to append in here, and the next request to our OpenAI or whatever the bot, like whatever the frontier LLM that we are doing, it will be chat completion with all the messages. So you see, after this messages, we just keep on appending it again and again. So it is nothing but a state management. It- the the part that we have to be very careful is we are not losing the state in between, like user can because it is being controlled by the browser or any client application. This state will be the of paramount importance to us. So here the user that like let's take a complete architectural overview how it generally happens and how important is this state management or the conversation manager. Generally, this is one of the common class you will see in any of the program that you will be writing. Will be a conversation manager. So what it will do is it will keep on adding the user message, like what is the list comprehension in the same Python chatbot, and then it is going to generate a response. And of course, there will be some other part, like it is going to enforce some kind of a limit, like some kind of a sanitization, some kind of output verification, and then it will keep on adding it to our assistant. And then when the next message comes, it is going to get these things like the generate the user assistant user that we were talking about. It is going to call the OpenAI LLM. So the point that I am trying to make is it is very important part is this guy. So this guy is going to make all the important calls that how I am going to handle the state of this conversation. So if I just take a little deep dive into this conversation manager, let's take into this real world backend engineering problem. Like this is not something made up, but many organizations that I know of, they have done this sort of a thing, like from OpenAI or Anthropic for some of their data privacy needs, like especially the healthcare bot that are being there, they are going into the self-hosted model. So suppose it can be like the Llama 370 billion model or a Quen or anything where they are self-hosting the model. So about the self-hosting, I think you got some idea when in the previous video we talked about Olama, right? So in the same way, we could just self-host our particular model. It is not as simple as that, but the overall idea is quite same. You pull that particular image of the large model and then you run it locally. Okay, so suppose for some sort of a data privacy needs, this is something we need to do. But one of the thing that we earlier discussed is the way the conversation manager is handling everything. There is a certain JSON format or certain role user, this sort of a format it is maintaining. So in our current code base, the things are probably like this, where we are having some a lot of microservices which are doing it in this pattern, like the role system and content, and you are basically a JSON parser. And whereas as a user, you are passing this thing to your ChatGPT OpenAI model. But in Llama 3, what would happen is the this particular prompt that we are sending, it has to be in a completely different way. So there is a certain header ID, there is a certain JSON parser. So rewriting all these microservices that you have created for this chatbot, then it will be very difficult, right? So how do you architect this system to support both OpenAI Llama, or suppose you are building something like our Perplexity. Okay, so in Perplexity you have combination of all the things like the Gemini or Kimi. Then there are uh, of course OpenAI, Claude. So, so how would you support everything like in your same layer, because you do not really know this part. So code wise the implementation is quite simple. You generally write a adapter or a factory pattern. Here the low level design things are coming. So that is why like this low level coding is not going anywhere, guys, unless you understand this nuances that these are three or four different models that I need to serve, and they might be having a variable in terms of their JSON structures and many other things. So how do you design it as a developer? So here, using the simple factory pattern, we can do it. And how the code generally looks like is, I'm not going to give you the not going to write you the complete code right now. But suppose you have a factory, and inside that factory you have a different adapter, like your OpenAI adapter, your Llama adapter. So what it is going to do is, whatever the messages that you are going to send, it is going to uh, change the message according to that adapter, and then further it is going to send it to the LLM. So that is in a very high level how it would be. So these are like the real world software engineering challenges that we still have to solve, no matter how much we say that LLM is taking over the coding. Yes, of course, this part probably it will tell you that how you can write, but unless you are aware that using adapter or factory, you can achieve this sort of a thing with a code modularity, with a zero business logic change, you will not be able to direct, if you are using cursor or cloth code, whatever it might be, as your as your coding assistant agent. But these are the basic things we need to understand. So now let's start going gradually into the little bit further deep into this prompt engineering, from the fundamentals to a little bit more deep. So when we are saying about the prompt, there is a certain hierarchy of control is being maintained. So what exactly is a hierarchy of control? Let's This term somewhere down the line you might have heard. Like, the first one is the zero shot. Zero shot means it is a single instruction. Suppose you are just asking instruction solve this problem. Whereas the few shot is more like show the model examples of what you want. Like, you want a certain solution to a mathematical problem, but you want the theory at first, and then probably you want some of the hint how you can solve it, and in the end you want that hint to drive you towards solution. So that is what a few shot or a pattern demonstration uh, pattern demonstration methodology, we can say, which defines that showing the model examples of what exactly you want. So it is more like, here are the examples, and from there you infer the pattern and take the uh, take the route towards the answer. Instead of directly giving the answer in the LLM way, you completely drive the LLM towards this answer. And another one you already know, which we discussed, that is the system prompt. So when we are saying this hierarchy, so we can maintain this hierarchy in multiple ways. So zero shot prompting, I think you already got the idea that any general knowledge queries, when we are talking about any general knowledge query sort of a thing, that goes as a zero shot. Okay, and the weakness is like, for the zero shot, it is a very high variance of output. Like, I don't really know what would be the output. I do not control, as like, when I am passing something to the function, I am not really controlling what would be the output. So there is a very high variance. It can be anything, like it can take you to any direction for that particular answer. So given that, the main, like, the weakness of this system is it provides you a very high variance one, and another one is this cause this sort of thing only, like when we are giving zero shot prompting. The models, they often start hallucinating when we if it doesn't have any particular forma or particular pattern to follow. So the example would be like something like a name demonstration. For example, if I take this, extract the name from my name. Okay, so this is the instruction that I have given. Extract the name from this, that my name is Alice Johnson. And over there, you see the way the JSON is getting returned, it is the name and Alice Johnson. But the main problem is this output format, if you see, it is unstable. Like sometimes it is clean. For example, like it can give you just Alice at times, or if some model are being trained to identify only the surname as a the actual name, then it might give Johnson. Uh, so the answer can be this either Alice or this like Johnson. Okay, or here we have seen the Alice Johnson. So this is kind of a unstable thing. Now, in case of a few shot prompting, how it would be, it is very, very interesting and very contrasting if I just show you. So, you are going to provide a input output example pairs before the actual task, and model infers the transformation function from that. So, like it will be clear from the actual example, the same task I asked that guy to perform earlier as a single shot, I can just keep on breaking it in this way. For example, here I am asking that as a assistant, this is the form of output that you should be getting. For example, uh, the content should be like, if my name is Alice Brown, you should put it as Alice Brown only. Some user is giving a different sort of a extract, like I am Bob Lee from NYC. Okay, so here you are giving the another example to this guy that you extract the name of Bob Lee. So here you see this is Charlie Wilson speaking. This is again a different sort of a sentence that you are passing, but you are telling the assistant that you take only the Charlie Wilson. So by this time, when you have given like three examples, this guy would be like would be able to understand the pattern in some way. So now the actual query that you have is like, my name is Alice Johnson. So now it is going to be consistent. So if you are programming something like this, it is very important that whatever the response that you are expecting, you give it in a given format as a pattern example, so that by showing these three things, uh, we will be able to achieve the exact format, and while consuming it will be very easy for you to um, you to parse that output. You do not have to clean up much. So over here what we have achieved is, the first thing we did is we have defined the output format, which is very very essential for the application developers, because out other than you have a definitive output format, you cannot really go into a multi-branch sort of a logical statement that we will gradually come into that when we will go into the agentic orchestrator in our later videos. But this is one of the very important use case, that if you have a definitive output format, then only you could use it as a switch block or in your if else statement, and take a branching decision on based on that. Okay, and this of course is like it eliminates any wrapper text. Okay, so when you are eliminating the wrapper text, at that particular scenario, the favor that you are doing to your system is you are using less tokens, right? So the more tokens means it will be more problematic, although during your prompting probably you are sending a little bit more token, but down the line with the accuracy and with the by cutting off all the wrapper text, you are already making sure that it is completely taken care. So with this, I hope you understood the multi-shot, the few shot, or the multi-shot and the zero shot. Now I'm not going to the system prompt in detail, because system prompt we already covered like in our previous sections when we have been discussing that how, what is the important of the role, the content, the assistant there, how do we define the system prompt. So system prompt is basically one of the God mode instruction that it sets the global tone or the behavior of, suppose you are building a bot or you are building a image extraction model. So at the top level, this system prompt will be there. So now let's come into the next section, that is a chain of thought. So if you remember, like last time when the DeepSeek came for the first time into the mainstream frontier model picture, it took the market with a completely strong storm that how exactly you could build a chain of thought or a difficult reasoning towards taking a decision. But LLM traditionally was failing at the multi-step reasoning, and DeepSeek somewhere down the line completely solved the problem. But if you see, uh, by design, it only made sure few of the fundamentals tweaks are perfect, and on top of it, it implemented the chain of thought. So this is a very important thing, guys, in case like towards our agentic journey. In case you are looking to build your agent, this is going to be one of the gold concepts for you to get started with. So the problem that we often face is whenever you have an LLM, okay, and which required like multiple logical step, and we expect the immediate answer, accuracy most of the time drop. Like it has to be a little bit complex with 10 to 12 different parameters to consider, and also alongside that you might need to pull data from some resources and then take those data into consideration at the time of giving answer. So those sort of cases, like a little bit of complex scenarios, you might see that there is a drastic drop in the accuracy. So for example, like one of the very popular example which were running during the GPT 3.5 days, like 2022 November. I remember I even tried this one somewhere. That is 9.11 is greater than 9.8. The practical answer is yes, but like no. So like the LLM answer is yes, but the practical answer used to be no. So why this thing fails? So let's understand it by writing it, so that we do totally understand the thought process behind it. So first of all, the model generates the token sequentially, right? That we already uh, learned in our previous videos. The tokens. Then what would happen is the output would be yes after seeing, uh, because initially what happened is models are trained, or like I would say were trained to treat everything as string. Okay. So what was happen is, like if you see here, it is calculating 911 and versus 98. Okay, so this was one of the very early days problem of any kind of transformer that we were having. So although like over the time, if you unless you direct very explicitly that you treat it as a number, like if I make this statement change, like is 911 as a number, like if I mark it as a is 9.11 as a number greater than 9.8, then you will get the answer no. Okay, because it is treating this thing as a number. But the moment is it start treating this thing as a basic string integer, how the earlier frontier models were designed, so it will fail in that case. So how do I handle this sort of scenarios? So we inject a instruction which would require step by step analysis, something like this. Probably like the prompt will be way more complicated, but it is, if you put something like this, you will be able to achieve the basic chain of thought. Like at first we are asking them to analyze the problem, then we are asking it to break it down, and then we are asking it to solve each part and then provide the final answer. So with this approach you will see that 911 9.11 will not be greater than 9.8 if it is treating it in this way, because during the analysis of the problem only it will be able to convert all of these decimals to convert the strings to actual decimal numbers. And then it is going to further break it down and then solve the things and then giving you the final answer. So now earlier we know why it fails. Now why it would work here, why it will work, because of the analyze. In the first or the initial step only you started analyzing it, and whatever the tokens that you are getting, the model is essentially dumping some intermediary step to the context window for the next one to use. So the tokens to be used by next steps. Okay, and then again the subsequent stages, they build on the reasoning token. So analyze is basically like the way uh, the way the LLM and the chat world see is these are the reasoning tokens, and on top of the reasoning token, the next steps are build. Okay, so here we got this thing. But again, the flip side of it is the amount of cost that you have to incur. So if you remember DeepSeek in the earlier days, it used to be very slow whenever you go into the deep think. Okay, whenever you go into the deep think or the reasoning mode, it is to be very very slow, and like oftentimes, like I remember when I was using it, it used to say that it cannot really it cannot really proceed with that because it became so famous. Many mathematicians and the people, they were using this reasoning mode, and this reasoning mode, the main issue it comes with that is it will generate way more tokens. So it used to generate like almost 10 time token what the general chat GPT used to generate that time during the API calls, and so the cost also used to be 10 times, but the accuracy was very high. Like here, whatever the numbers that it is giving, it is very close to the actual production experiments and the benchmark that the many organizations have run. But this is kind of a trade-off that we as a developer, we have to propose it to our product managers that what do you want me to optimize for, whether you want to optimize for the cost or you want me to optimize for the accuracy. So based on that, we are going to get this particular answers. So in case you have understood till this point, it's like I'm sure you have done a very good job, because there are a lot of things we have covered, and I know the video has gone really long, but this was very necessary to set you the main importance of the prompt and the prompt engineering as a system design. So prompt engineering is a, like, when we say from a business perspective, it's a completely different thing, but when we are thinking from the system design perspective, it's an entirely different thing. Like cost, latency, the chain of thought, everything has so many things to consider before implementing. I hope you are able to get a complete picture. So in our next video, we will go into the way more advanced orchestrator technique. Like chain of thought is still, I would say, one of the basic level of orchestration technique. It is kind of a orchestration, but there are way more other techniques that are being there. So we will try to concentrate upon those things, and so see you in my next video. Let me know in case you have any doubt in my comment section. I will try my level best to answer them. So wait till my next video. Till then, stay awesome. Bye.